Hello students. Now on this last video we will look at two key concepts. We will look at ice tables, which are dealing with equilibrium when we do not necessarily know equilibrium concentrations, and we will look at Le Chatelier's principle. Normally I would split these into two videos, but Le Chatelier's is simple enough and quick enough. It doesn't necessarily need its own video. With that in mind, we will look at these two key concepts. So, idea that when we know equilibrium concentrations, it is relatively simple. But in a real world situation, we may not know all the concentrations of every vast species. At best, we might know one or maybe two, because one or two glows or absorbs wavelengths of light, or we have some way of figuring out a concentration. But as long as we know the initial conditions, we can figure out what the conditions at equilibrium are. We have to use a little bit pre-calculus. We have to use a concept called an ICE table, or ICE table, where we can solve for our K expression. Our ICE table stands for initial change and equilibrium. The idea behind this is that at initial states, at initial conditions, we're making the assumption we are mixing these guys together, and before the reaction starts, we have no product. Before the reactions begin, we have no product present. Because equilibrium must establish, the products must start to form, and the reactants must start to be consumed. So we know when Q equals 0, Q is always going to be less than K, so the reaction must proceed towards products. Now, how much that proceeds depends on the size of K. But the idea before the reaction even begins, Q always equals 0, and then, so we know it's proceeding towards products as it does so. And so we can put a generic subtract X from our reactants, where X is 1 mole or some generic X moles of reactants. And we can add an X into the products, where X is the number of moles of products that will be formed. And equilibrium is just the sum of those two steps. You add the initial to the change, and that will be whatever the concentration will be at equilibrium. So the situation I have given you in this first slide is that iron is more or less colorless, a little yellowish. Thiocyanate is colorless, but when I mix them together, we form a iron thiocyanate complex that is vivid red. You'll be able to tell it's formed. It absorbs wavelength of light very strongly. You can measure this. We'll probably measure this in lab by UV-vis spectroscopy, and the reaction is simply as follows. So iron plus thiocyanate goes to iron thiocyanate. So products over reactants. Pretty easy. Well, if we know the concentrations initially, and we measure the concentrations of thiocyanate, it's not thiocyanate measured is equal to the X, because 0 plus X is just X. So if we know the concentration of thiocyanate, iron thiocyanate, we can figure out what is the thiocyanate at equilibrium. So I'm going to take the 3 times 10 to the negative 4th, and I'm going to subtract out my 5.46 times 10 to the negative 5th. And I can subtract that number also from our iron. So 5 times 10 to the negative 4th minus 5 times 5.46 times 10 to the negative 5th. And we got our values. That was pretty simple right there. We just had to subtract out those from there. So you get a K expression is 500. But sometimes things aren't so simple. Looking at this, if I initially put in 3 atmospheres of hydrogen and 1 atmosphere of nitrogen, 3 atm hydrogen, 1 atm of nitrogen, and I want to know what is the Kp if after equilibrium establishes we get 0.706 atmospheres of ammonia. So let's look at that. With that in mind, okay, let's go to the document camp. So we have 3 H2, 1 N2 goes reversibly to 2 NH3. Now, since this will go towards products, we need at least some loss of nitrogen. 1 mole worth of nitrogen, but for every 1 mole of nitrogen, we would produce 2 moles of ammonia. For every 1 mole of nitrogen that reacts, we would lose 3 moles worth of hydrogen. So at equilibrium, we're going to add those together. So 3 minus 3x, 1 minus x, and 2x. And so right now, it's in our K expression. Our K expression is essentially, if I didn't evaluate 2x squared, 3 minus 3x cubed, and then 1 minus x. However, we know x because we know this concentration. So 2x is equal to 0.706. So x must be equal to this number divided by 2. So x, 0.706 divided by 2, x is 0.353. So 1 minus 0.353 is 0.647. And 3 minus 3 times 0.353 is 1.941. So with that in mind, 0.706 squared over 1.941 cubed and 0.647 would give us a K expression of 06 squared 7.941 cubed 0.105. So just by mixing in 3 atmospheres and 1 atmosphere, most of the hydrogen, a lot of the hydrogen, well, 1 atmosphere of hydrogen's gone away, 0.3 atmospheres of that's gone away, and we produced about 0.7 atmospheres of that. So, pretty straightforward. You just have to plug that in. Now, when K is known, things can be a little bit nicer, but it can be a little bit harder. So looking at this ice equation, if K is known and the initial concentrations are known, equilibrium can be determined via the ice table as well. So for example, a 0.25 molar solution of hydrofluoric acid has an equilibrium constant of 7.2 times 10 to the negative fourth. What is the concentration of H plus that must be present at equilibrium? So how much must this dissociate? Well, we're going to assume there's essentially 0 and 0. So 0.25, all the H plus and all the F minus are coming from H. So 0.25 minus X is going to be our E for there, and 0 plus X is just going to be X. So setting up our K expression, X times X over 0.25 minus X is equal to 7.2 times 10 to the negative fourth. Well, one way to go about solving this is the quadratic equation. One way to go about solving this is the quadratic equation, where the quadratic equation looks at a x squared plus bx plus c. And it always gives you two solutions where the quadratic would essentially cross the zero line. So you're finding the x values that would give you a 0 for y for this quadratic equation. Now, if we solve this, we could solve it via quadratic. It's doable and a little bit tricky, but it can be done. Yeah. But we can, by plugging, so how you would get the quadratic, set that up, is to cross multiply that 0.25 minus x to the k value. And so that would help give you your c value and your b value. And we could solve that, and please note that no matter what, even though the quadratic gives you two values, only one of them will be right. One of them will be wrong. One way you can know the one that's wrong, if you ever get a negative value for x, the answer is wrong. Or if you get a concentration that is larger than one of your initial starting concentrations, one where you can't subtract out more material than there are there. So either of those can be wrong. Now I want to show you a easier way to do this. An easier way to do that. Quadratic works perfectly all the time, but it is a bigger pain in the butt. The simplified constant, in order to simplify this in such a way, we're going to make an assumption that most times that x is small. X is going to be a small fraction of the initial concentration. And in that case, the error you're going to get with this assumption is very low. So you can check and take your initial concentration of a reactant and divide it by your K. If this is bigger than 400, then this is going to be a safe assumption. But so one way to do this is essentially this way, and I can show you how to correct this 100% of the time. But so we're going to do this solving by parts, or like, so what we're going to do is when we set this up, your K equals x squared over the starting material minus x. We're going to make the assumption that if that x is significantly small, that term drops to 0.25 minus 0, or essentially becomes a rounding error, and we can solve our x that way. If we go about doing that, we can see that, oh, the value I got for x, let's see, what did I, something. Let me see. Let's see. The value I got for x should not be too different from what I should have got. So let's see. That might be 1.8. 1.8 times 0.25. So, oh yeah, this is a different one. This is a different one. That's why I was thinking, why do I have a different answer? Another way to go about doing this, is, let's look at, I want to go back and look at these. I will show this -4. I will show this, the other one, 7.2. E to the -4. And the correct answer is 0.0131, and the correct answer is 0.00671. I want to show you another way to do this that essentially works what I just did. So we're going to solve this in parts, and it's simply what I just did, except takes it one more step further. We have our K expression. So our K expression, we have our initial concentration, our reactants, 0.25, 7.2 E -4. Our products, P1, P2, is going to be 0 and 0. So this is technically supposed to be 0.25 minus X. We don't know what that is. It's going to be X. This is going to be X. X. So just do that. So we're going to make the assumption. Let's solve this where it's just x squared over 0.25 and solve that for K. So let's do that. So x squared is equal to K, our value here, times 0.25. We got a value. Okay. Now we're going to square root this. So type equals SQRT, and I'm going to put the square root. There is my. So my correct value should be 0.0131. You'll notice it's slightly different. But so we've done that first time. Now here's the little trick. I'm going to do it. What happens if I say 0.25 minus 0.131416? Now I'm going to try to solve it a second time with that value. So my x squared, my new x squared, is going to be equal to my K value, and I take my new equilibrium concentration of reactants. So I got, instead of 1.8, it's 1.7. I take the square root of that, and what is my new value? 1.3051, which rounds to 0.131. And I could do this as many times as I need to. So what about if I took 0.25 and I subtracted this guy? I got a slightly different one, and so what's my new x squared? So you're solving this multiple times, slowly tweaking your value. So square root, and each time we tweak it, it changes a little bit more. So this went up to 0.013062. So right there, that's about as close as that's going to get. That's closest to the correct answer. Looking at the same thing, doing the same thing with the other value. So 0.25. What about 1.8 e to the -4th? Okay. There's our K. There's our R. So let's say, we'll just say our x squared is going to be equal to our K times our R. Our K value times our R value. And so, and 0.25 minus x. We square root this. Square root. Okay, get that. Let's try this now. Equals 0.25 minus this value. And then try it again. X squared is equal to this value times this value. And we square root. And we'll find out how close did we get. 0.6618. So it slowly tweaks it more in the correct direction each time. This, you're just running it, your R times your K, and then you square root it, and then you use that value for your concentration minus X. If you do this, do it once, maybe do it a second time, it will help get you a closer answer without having to do the quadratic. This will get you the right answer each time, and it's a lot easier than using the quadratic. However, if you want to use the quadratic, that is fine. But this will guarantee you get a right answer, and it's another way to do it. With that in mind, let's continue on. The last concept is Le Chatelier's principle. It's a statement that simply states that by disturbing equilibrium, nature tries to reestablish equilibrium by shifting Q so that it once more equals K. The idea here is that for example, the Haber process. The Haber process is the way we produce ammonia on an industrial scale. That nitrogen plus hydrogen gives you ammonia. Based on that alone, that only gives you 35% yield. There's a lot of nitrogen and hydrogen waste that would not be very useful for using in any sort of large-scale system if we could not find a way to make it give a higher yield. This is one of our key productions of ammonia, far more than what nature normally produces other than like nitrogen fixating bacteria. And so a clever French chemist by the name of Henri Louis Le Chatlier proposed this principle of how by disturbing equilibrium we can force nature to compensate. And so the Haber process was utilization of this Le Chatelier's principle on an industrial scale. The idea is that when the reaction's at equilibrium, no more product is essentially being formed. However, if you upset the equilibrium, so you change Q so it no longer equals K, Q will have to shift, and so K equals. It will auto-correct so that Q gives me more K. Now, K only changes with temperature. So for a given reaction, there will not K will not change with a concentration. But what will change is Q. So whatever you do to the reaction changes Q, and thus reaction will always shift until equilibrium is reestablished. So, for example, if you add a reactant, you are making Q smaller, and so reaction shifts towards products. When you add a reactant, reaction removes the reactant and converts it to product. If you add a product, however, it will, without changing anything else, reaction will shift backwards. The same thing can be accomplished through removal. If you remove a reactant, the reaction tries to produce more reactants to replace it. But if you remove a product, the reaction shifts to replace the product that you have cleverly removed. The reaction is going to shift to undo the changes. Now, there's other ways to do this. We can change pressure and volume. This pressure and volume only affects gases, but if you change pressure, you're going to try to fix the change. So if you increase the pressure, the system's going to shift in ways to reduce the pressure that you've upped. So we're going to shift towards less gas molecules. You pressurize something, you're going to try to get less gas molecules. And so it's going to shift away from the gas molecules. But the same thing occurs when you decrease the volume, because volume goes down, pressure goes up. But if you decrease the pressure, it shifts to the side with more gas molecules. So if you look at a can of soda, it is highly pressurized in a small volume, so a lot of CO2 dissolves as carbonic acid. You open the soda, you release the pressure, and you increase the volume to this whole room. Suddenly, the soda starts to go flat as we shift towards a lower pressure system. We shift towards more gas. But please note, in these situations, K is still the same. The other way is to change the temperature. Changing the temperature will shift equilibrium. Changing the temperature changes K. So Q doesn't actually change in this one. You're either moving K up or moving K down, and the reaction shifts to fix that. And the direction K changes depending on whether a reaction is naturally endothermic or exothermic. You can think of it endothermic as heat is a reactant, and exothermic is heat as a product. If you are increasing the temperature, you're adding heat. So if enthalpy is a reactant and you add heat, the reaction shifts to products. If heat is a byproduct, adding heat will force it back to reactants. If you decrease temperature, it's going to endothermic is going to make more reactants. Decreasing temperature, exothermic makes more products. This is the only way to change K. So looking at that same Haber process, which is exothermic, if I start pumping in more hydrogen, what's going to happen? Well, you should expect this increases the products. If I remove ammonia by converting it into a liquid, it should increase the products. If I decrease the volume by pressurizing this, there's 2 moles of gas on the right and 4 moles of gas on the left. So decreasing volume increases pressure and forces it to the right. And since it's exothermic, if I remove the temperature, I'm favoring product formation because I'm removing a product. The only thing that does not change is the catalyst. The catalyst makes it go faster, but it does not make more products or more reactants. It just gets equilibrium faster. So what they do is they remove temperature and condense the ammonia as they highly pressurize more hydrogen and nitrogen, and they can produce large amounts of ammonia that can be used for different industrial processes or in fertilizers. And that's the basics of this chapter. But that's the main concept we will build upon: equilibrium and Le Chatelier's. With that in mind, have a good day.